Tonight, something is happening above your head that most people will completely miss. The moon is full, not just full in the loose, casual sense we use when we glance up and say, "Oh, that's a big one." Full in the precise astronomical sense, peak illumination, the exact geometric moment when the sun, the earth and the moon line up so perfectly that the lunar surface blazes with maximum reflected light. But here is the thing that makes tonight genuinely unusual. The moon hit that precise peak today, May 1st, 2026, at 13 minutes past 1 in the afternoon Eastern Time. Not at midnight, not at 3 in the morning when the sky is dark and the world is quiet. In the middle of the afternoon, while most of North America was eating lunch, sitting in traffic or staring at a spreadsheet, the moon quietly reached the most perfectly full moment it will achieve all month, and it did so in broad daylight. This is the flower moon. And its story is stranger, older, and more beautiful than almost anyone realizes. To understand why any of this matters, we need to talk about what the moon actually is when it is full, and why the timing of that fullness changes everything about how we experience it. Most people carry a vague mental image of the full moon as something that happens at night, something that rises as the sun sets, hangs in the dark sky until dawn, and then disappears. And for a lot of full moons, that image is close enough to true. But the moon does not actually wait for nightfall to become full. It reaches peak illumination at a specific second in time, and that second is completely indifferent to whether your half of the planet is facing the sun or facing away from it. Think of it this way. The moon orbits Earth continuously, completing one loop roughly every 29.5 days. As it moves through that orbit, the geometry between the moon, the Earth and the sun shifts constantly. When the moon is between us and the sun, we call it a new moon because the lit half faces away from us, and we see only darkness. As the moon moves around to the opposite side of Earth, more and more of its sunlit face turns toward us, crescent, then quarter, then gibbous, and finally, when the moon has travelled all the way to the far side of Earth from the sun, with Earth sitting almost directly between them, the entire sunlit hemisphere of the moon faces us at once. That is a full moon. That moment, that precise geometric alignment, arrives on a schedule that has nothing to do with clocks or time zones, or whether anyone is awake to see it. It is as fixed as a heartbeat, and this month it arrived in the early afternoon. For people in North America, this means something counterintuitive. The moon was technically, astronomically perfectly full, while most of us could not even see it. It was above the horizon for some locations, skulking low in a bright blue sky, nearly invisible against the daylight. For others it had not even risen yet. The most full the moon will be this entire month happened while the sun was still ruling the sky. And yet tonight, when the sun goes down and the sky darkens, the moon will rise and it will look spectacular. It will look full. It will look like the kind of full moon that people take photographs of and post online and describe as the most beautiful thing they have seen in months. But here is the secret. By the time you see it tonight, it will already be slightly past full. By a few hours, technically. The peak was already behind it. Does that matter? In terms of how it looks to your eyes, almost certainly not. The human eye cannot detect the difference between a moon that is exactly full and one that is 99% illuminated. The moon tonight will be stunning, but there is something quietly fascinating about knowing that the true mathematical peak, the most perfect fullness, happened while most of us were going about our daytime lives completely unaware. Now, let us talk about the name, the flower moon. Where does it come from, and why does it belong to May? The practice of giving each full moon a name rooted in the natural world goes back centuries, woven deeply into the traditions of multiple indigenous nations of North America. These names were not decorative or poetic in the way we might use them today. They were practical. They were part of a living calendar, a way of tracking time through the observable world rather than through numbers printed on paper. May, in much of North America, is the month when flowers burst into bloom after the long dormancy of winter. The landscape transforms. Meadows that were brown and frozen fill with colour. Trees that stood bare and skeletal for months suddenly erupt in blossoms. The world is visibly, obviously, dramatically renewing itself, and so the full moon of May carries the name of that renewal. The flower moon. Different nations use different names for this same moon. Some called it the corn planting moon, marking the time when crops could safely go into the warming earth, Others used names tied to the return of certain animals, the songs of particular birds, the height of rivers swollen with snowmelt. Each name was a snapshot of the natural world as it appeared to people who paid close attention to it across generations. Colonial American farmers and settlers adopted and adapted many of these moon names, and they eventually filtered into almanacs, newspapers, and the popular imagination. By the time the Old Farmer's Almanac began publishing in the late 1700s, names like the flower moon and the harvest moon had become part of the shared cultural vocabulary of North America, disconnected from their original indigenous context, but carrying forward a recognition that the night sky and the living earth are part of the same continuous story. Today, those names have been reclaimed and amplified by social media, by astronomy enthusiasts, by anyone who finds beauty in the idea that a full moon is not just an astronomical event, but a moment embedded in a specific season, a specific landscape, a specific relationship between human beings and the world they live in. But the flower moon is just one part of what makes the May full moon remarkable. To understand the rest, we need to go back roughly 4.5 billion years to the origin of the moon itself. The leading theory for how the moon was born is called the giant impact hypothesis, and it is exactly as dramatic as it sounds. In the early solar system, the neighbourhood around the young sun was chaotic. The planets were forming from swirling clouds of dust and gas, growing slowly through endless collisions. Earth was taking shape, building mass, slowly differentiating into a dense iron core surrounded by silicate rock. But Earth was not alone at its distance from the Sun. Another body was forming along a similar orbital path. Scientists believe it was roughly the size of Mars, perhaps 40% the mass of early Earth. We have given this long-vanished world a name, Theia, after the Titan of Greek mythology, who was the mother of the moon goddess. Theia and early Earth shared an orbital path for millions of years, their gravitational relationship keeping them in a kind of uneasy balance, and then something shifted. Gravitational perturbations, the slow accumulation of small nudges from Jupiter and the other giant planets, destabilized Theia's orbit. The two worlds converged. The collision, when it happened, was not a clean Hollywood-style explosion. It was a prolonged, grinding catastrophe that played out over hours. Theia struck Earth at an oblique angle, a glancing blow that sent material spraying into space in an enormous arc. Both bodies were partially destroyed, their mantles mixed and vaporized. A massive cloud of molten rock and vapor was flung into orbit around what remained of Earth. Over thousands of years, that orbiting debris gradually coalesced. Gravity pulled the scattered material together. Droplets of molten rock merged with other droplets, growing into larger and larger masses, eventually forming a single spherical body, the Moon. Early in its history, the Moon was dramatically different from what we see today. It was much closer to Earth, perhaps 10 times closer. From the surface of early Earth, the Moon would have appeared enormous, looming in the sky like something out of a fever dream. It was also molten, its surface a global ocean of liquid rock, glowing with residual heat, bombarded constantly by debris left over from the violence of its formation. The Moon has been cooling and solidifying and moving slowly away from Earth ever since. That last point deserves a moment of attention, because it changes how we think about the night sky tonight. The Moon is not stationary. It is not frozen in place at some fixed distance. It is drifting away from Earth at a rate of roughly 3.5 centimeters per year. The width of your hand. Every year the Moon retreats a little further. This drift is caused by something called tidal friction. The gravitational pull of the Moon raises tides on Earth, not just in the oceans, but in the solid rock of Earth's crust itself. These tidal bulges create a slight asymmetry, and the interaction between that asymmetry and the Moon's gravity transfers energy from Earth's rotation into the Moon's orbit. Earth's spin slows down imperceptibly. The Moon moves outward. In the distant past, the Moon was close enough that it raised tides many times higher than anything we experience today. The gravitational interaction was intense enough to slow Earth's rotation dramatically. A day on early Earth may have lasted only 6 hours. As the Moon retreated and Earth's rotation slowed, days grew longer. 1 billion years ago, a day was probably around 18 hours. And in the future, that process will continue. In the very deep future, billions of years from now, if Earth and the Moon both survive the eventual expansion of the Sun, the Moon will be far enough away that total solar eclipses will no longer be possible. The moon's disk will be too small to fully cover the sun. The coincidence that currently makes total eclipses possible, the fact that the sun is 400 times wider than the moon but also 400 times farther away, making them appear the same size from Earth, is temporary. A gift of this particular moment in deep time. We happen to live during the window when that coincidence holds, during the window when the moon is close enough to produce total eclipses, far enough to be a gentle companion rather than a tidal tyrant, and old enough for its surface to be a stable, ancient record of the solar system's history. Speaking of that history, let us look up at the moon tonight with fresh eyes for a moment. The surface of the moon is divided broadly into two kinds of terrain, the bright, heavily cratered highlands and the dark, smooth regions called maria, which is the Latin word for seas. Early astronomers named them seas because they looked, through small telescopes, like bodies of water. They are nothing of the kind. The maria are ancient lava plains. They formed between roughly 3.5 billion and about 1 billion years ago, when volcanic activity flooded enormous impact basins with molten rock. When the lava cooled and solidified, it left behind the dark, relatively flat surfaces we see today. The highlands are older and more cratered, because they have been accumulating impact scars for a longer time. Every crater you can see on the moon is a record of a collision, a meteor or asteroid that struck the lunar surface and excavated a bowl-shaped depression. The moon has no weather, no plate tectonics, no erosion in the traditional sense. A crater that formed 3 billion years ago looks almost exactly the same today as it did the day it was made. The moon is a museum, a frozen archive of the early solar system. Some of those craters hold ice. This discovery, confirmed definitively in the last couple of decades by orbiting spacecraft and instruments that bounced radar signals off the lunar poles, revealed that the moon is not as dry as scientists once assumed. In permanently shadowed craters near the poles, regions that have not seen a single ray of sunlight in billions of years because of the moon's slight axial tilt, temperatures drop to the coldest found anywhere in the inner solar system, cold enough for water ice to survive indefinitely. This ice is almost certainly ancient. It may have been delivered by comets and asteroids over billions of years, gradually accumulating in those eternal shadows. It represents a resource with enormous implications for future exploration. Water can be split into hydrogen and oxygen, providing breathable air and rocket fuel. Permanently shadowed craters near the poles could become staging grounds for extended human presence on the moon. The missions returning to the lunar surface within the coming years are targeting precisely these regions. The poles are where the resources are. The poles are where sustained exploration becomes possible, rather than merely symbolic. And this brings us to something worth sitting with for a moment. We are living in a period of renewed attention to the moon, unlike anything since the 1970s. Multiple national space agencies are actively developing lunar landers. Commercial companies are building robotic prospectors. There are serious funded plans to establish permanent outposts on the lunar surface within this decade. The moon that billions of people will look up at tonight, the flower moon hanging low on the horizon and blazing with reflected sunlight, is the same moon that is currently the focus of the most ambitious space exploration program in half a century. It is simultaneously ancient beyond easy comprehension and urgently contemporary. What is it like to stand on the lunar surface and look back? 12 human beings have done this, all of them American, all of them men, all of them during a 6-year window between 1969 and 1972. Every one of them described the experience in terms that strained against the limits of language. The sky above the moon is black, not dark blue, not deep purple, black, absolute. Because the moon has no atmosphere to scatter sunlight, the sky is space itself, and space is black. During the lunar day, when the sun blazes with unfiltered intensity, the black sky and the blinding surface exist side by side in a contrast that human eyes have no prior experience for. There are no soft transitions, no gradations, hard shadow and harsh light, with nothing in between. The horizon curves. The moon is small enough that even standing on a flat plane you can sense the curvature, the surface falling away noticeably in every direction. It creates an uncanny feeling of being on top of something rather than simply on something. And then there is Earth. Every astronaut who walked on the moon described looking up at Earth as the most profound moment of the experience. Earth hangs in that black sky, blue and white and impossibly colourful against the monochrome grey landscape. It does not rise or set the way the moon appears to rise and set for us. Because the moon keeps the same face pointed toward Earth at all times, a result of the same tidal forces that are slowly pushing the moon away, Earth stays nearly fixed in the sky from any given point on the lunar surface. It hangs there, it glows, it looks alive in a way that nothing in the surrounding void does. The tidal bulge on the side of Earth facing the moon does not sit exactly beneath the moon. Earth rotates faster than the moon orbits, so the bulge is carried slightly forward, ahead of the moon, in the direction of Earth's rotation. The moon's gravity pulls backward on this forward-displaced bulge, slowing Earth's rotation infinitesimally. But by Newton's third law, the bulge also pulls forward on the moon, accelerating it slightly in its orbit. When an orbiting body accelerates, it moves to a higher orbit, so the moon drifts outward. This is the mechanism. Earth loses rotational energy. The moon gains orbital energy. The day gets longer. The moon gets farther away. Everything is conserved. The universe does not offer free lunches. The rate of this drift, as we noted, is about 3.8 centimeters per year. That sounds trivial. But run it backward and you get a moon that was once much closer, raising tides of terrifying scale, possibly hundreds of meters, crashing across early continents with a regularity and force that is almost impossible to imagine. Run it forward and the moon continues to retreat until, in the far future, it will appear smaller in the sky. The geometry that produces total solar eclipses, the near-perfect match between the apparent sizes of the sun and moon as seen from Earth, will eventually be lost. Future civilizations, if there are any, will experience only annular eclipses, the moon a dark disk slightly too small to cover the sun completely. We live in the narrow window of time when the moon is exactly the right size and distance to produce total solar eclipses. That is either a coincidence or a reminder of something. What it reminds you of is up to you. Now I want to talk about water. The moon's poles are cold. Not because the moon has no atmosphere and heat radiates freely into space, though that is also true, but because the poles have craters whose floors are in permanent shadow. The sun never rises high enough above the lunar horizon to shine into those crater floors. They are among the coldest places in the solar system, colder than the surface of Pluto in some measurements, sitting at around negative 160 degrees Celsius in the shadowed regions, and potentially as cold as negative 240 degrees Celsius in the deepest cold traps. In those cold traps, there is water ice. We know this from multiple lines of evidence. The L-Cross mission in 2009 deliberately crashed a rocket stage into one of these permanently shadowed craters and observed the plume with a following spacecraft. The plume contained water vapor. Subsequent analysis found not just water but a complex chemical environment, carbon monoxide, ammonia, methane and other compounds, all preserved in the deep cold for potentially billions of years. Where did this water come from? The answer is probably multiple sources. Some came from comets and asteroids that bombarded the moon over billions of years. Some may have been produced by the interaction of solar wind hydrogen with oxygen-bearing minerals on the lunar surface. Some may have been delivered by the same processes that brought water to early Earth. The moon's polar ice is, in a sense, a record of the volatile history of the inner solar system, a deep frozen archive of impacts and solar activity stretching back billions of years. This ice matters for future exploration in a very practical way. Water is heavy. Launching water from Earth to the moon costs an enormous amount of money and energy. If water is already on the moon, it can support human presence, drinking water, water for growing food, and water can also be split into hydrogen and oxygen, the components of rocket fuel. A lunar base with access to polar ice has access to both life support and propellant, a foundation for sustained presence, and potentially for missions that depart from the moon rather than from Earth. This is why the lunar South Pole has become the focus of so much attention from space agencies around the world. It is not just scientific interest, it is strategic and economic interest in a resource that could make the difference between a brief return to the moon and a permanent human presence there. Look up tonight. The ice is there, invisible, waiting, in the dark places that the sun never reaches. Let us talk about what it costs. The Apollo program at its peak consumed about 4% of the United States federal budget. In today's dollars, the entire program cost somewhere around $150 billion, depending on how you account for it. It employed around 400,000 people. It was a national mobilization of industrial and intellectual capacity on a scale that has not been repeated. Artemis, the current program to return humans to the moon, is a different kind of effort, It is smaller in relative terms, though still enormously expensive. NASA's budget is currently around $25 billion per year, about 0.5% of the federal budget, a fraction of what Apollo required. The Artemis program involves international partners, commercial launch providers, commercial landers, and a more distributed industrial base. It is in some ways a more fragile and complicated enterprise than Apollo precisely because it depends on so many moving parts. But it also represents a different philosophy. Apollo was a demonstration. It proved what was possible. Artemis, at least in its stated ambition, is meant to establish something more lasting, a sustained human presence in the lunar vicinity, a gateway station in lunar orbit, periodic surface missions, eventual permanent infrastructure. Whether that ambition will survive the political and budgetary pressures that bear on any long-duration government program is genuinely uncertain. Space programs have been cancelled before. The Space Shuttle program was meant to make access to orbit cheap and routine. It did not. The Constellation program, which preceded Artemis and also aimed to return humans to the Moon, was cancelled in 2010 after years of development and billions of dollars spent. The history of human spaceflight is a history of extraordinary achievement, punctuated by cancellations, disasters, and long stretches of frustratingly incremental progress. It is also a history of people who kept working anyway. There are currently human beings living in space. Right now, as you read this and prepare to go outside and look at the Moon, there are people on the International Space Station conducting experiments, maintaining systems, exercising for 2 hours a day to prevent their bones and muscles from deteriorating in microgravity. There are people for whom Earth is a view out a window, a blue and white sphere hanging in darkness, the overview effect made into daily routine. There will be more of them. That seems likely. The question is how many, and where, and whether they will go far enough to stand on the lunar surface and look back at the small bright dot that is everything they have ever known. We are at an unusual moment. The first generation of moonwalkers is gone or nearly gone. Neil Armstrong died in 2012. Buzz Aldrin is still alive, in his 90s, the last surviving moonwalker, though others who flew to the Moon without landing are also still living. The generation that watched the moon landings live on television, who stayed up past midnight to see a human being step onto the surface of another world for the first time, is aging. The memory of Apollo is becoming history rather than memory. At the same time, the technology to return to the Moon exists, or very nearly exists. The rockets are being built, the landers are being designed and tested, the spacesuits are being redesigned. There is a real possibility that within this decade humans will again stand on the lunar surface and look up at a full Earth hanging in the black sky. When that happens, the flower moon will still be rising in May. It will still peak in the afternoon sometimes, quietly and without announcement. It will still pull the tides and stabilize the axial tilt and remind us, for those who are paying attention, that we live inside a system of extraordinary delicacy and improbable beauty. Look up. The tidal bulge does not sit directly beneath the Moon. Because Earth rotates faster than the Moon orbits, the bulge is always slightly ahead of the Moon, in the direction of Earth's rotation. The Moon's gravity is constantly pulling that bulge backward, trying to slow Earth's rotation. At the same time, the bulge's gravity is pulling the Moon forward, constantly accelerating it slightly in its orbit. When you accelerate something in orbit, it does not speed up in an intuitive way. It moves to a higher, slower orbit. The Moon is being pushed into a gradually widening orbit by the energy it steals from Earth's rotation. Earth slows down. The Moon drifts outward. This dance has been going on for 4.5 billion years and will continue for billions more. You can find evidence of this in ancient rocks. Fossil tidal rhythms preserved in sedimentary layers called tidal rhythmites allow geologists to count how many days were in a year at different points in Earth's past, because the Sun's gravity contributes its own, weaker tidal effect, and the interference pattern between lunar and solar tides creates a detectable signal in sediment. Rocks deposited roughly 600 million years ago suggest Earth had about 420 days in a year. Days were shorter, the Moon was closer, the whole system was wound a little tighter. There is something almost biological about this. The way Earth and Moon have been exchanging energy across billions of years, one slowing down, the other moving away, in a slow mutual negotiation governed entirely by physics. No communication, no intent, just gravity and time. Tides do more than shape coastlines. there is a serious scientific case that tides played a role in the origin of life itself. In the early Earth, before life existed, the oceans were a chemical soup. The building blocks of life, amino acids, nucleotides, the raw materials for the first self-replicating molecules, were dissolved throughout that water in extremely dilute concentrations. For any kind of chemistry complex enough to build life to occur, those molecules needed to find each other and interact repeatedly. In a vast ocean, randomly, that would take almost inconceivably long. But tides, the enormous tidal forces on early Earth, when the moon was much closer and tides were dramatically larger, would have pushed ocean water far up onto the continents with each cycle. In tidal pools, trapped water would evaporate, concentrating the dissolved chemistry. The chemistry would interact. The tide would return and dissolve the products back into the ocean. This cycle of concentration, reaction, and dispersal might have been the engine that drove the chemistry of life forward from dilute possibility to concentrated reality. If that hypothesis is correct, and it has serious proponents, then the moon did not merely stabilize the conditions for life over geological time. The moon may have catalyzed the origin of life itself. The tidal pools that might have been the birthplace of the first self-replicating molecules were created by the same gravity that is tonight pulling the ocean up along every coastline on Earth. Look up at the flower moon. There is a plausible argument that you would not exist without it, in a more literal and immediate sense than most people consider. Let us shift our attention now to something that has been quietly transforming our understanding of the moon over the past 2 decades, the systematic exploration of the lunar surface by robotic spacecraft. The Apollo missions were extraordinary. 12 people walked on the moon. They collected 382 kilograms of lunar rock and soil, brought those samples back to Earth, and launched decades of scientific analysis. We learned enormous amounts. But the Apollo missions covered only a tiny fraction of the lunar surface, 6 landing sites clustered within a relatively narrow band of the near-side equatorial region. The moon is enormous. The area surveyed directly by human boots was, in planetary terms, almost nothing. The decades after Apollo saw the moon neglected for a while, the political momentum that drove the space race dissipated, and the attention of space agencies turned toward Mars, the outer planets, and the deep solar system. But in the early 2000s, a new generation of lunar orbiters began systematically mapping the entire surface from above, building up a picture of the moon that is dramatically more detailed and more surprising than anything we had from Apollo alone. Some of the findings have been genuinely startling. The far side of the moon, the hemisphere that always faces away from Earth, is strikingly different from the near side. The near side has large, smooth maria, the ancient lava plains we were talking about earlier. The far side is almost entirely highlands, heavily cratered, with only a handful of small lava plains. For decades, this asymmetry was noted and explained in various ways, but recent analysis has pointed toward a fascinating possibility. In the moon's early history, when both bodies were still young and partially molten, the 2 hemispheres may have cooled at different rates. Earth's heat kept the near side warmer for longer. The far side cooled faster, solidifying into a thicker crust. When volcanic eruptions later flooded the moon's interior heat outward, the thinner crust of the near side allowed lava to break through more easily, creating the maria we see today. The thick crust of the far side resisted, leaving it largely unmodified. The near side of the moon is, in a sense, geologically shaped by Earth. Our presence in space influenced the geology of our companion world billions of years before any human being walked on it. There is a region on the moon's south pole, enormous in scale, called the South Pole Aitken Basin. It is one of the largest and oldest impact craters in the solar system. The basin is so deep that in some places it penetrates into the moon's mantle, exposing rock from far below the surface that would otherwise be inaccessible. Scientists are deeply interested in this region, partly because the mantle rock it exposes could answer fundamental questions about the moon's internal structure and its history, and partly because the rim of the basin, near the poles, is precisely where those permanently shadowed craters with their preserved water ice are located. There are mountain peaks on the rim of that basin that receive almost continuous sunlight. They are called peaks of eternal light. From them, you could see the sun on the horizon nearly 24 hours a day. Just a few kilometers away, in the deep shadow of the basin floor, temperatures would be colder than anything else in the inner solar system. That juxtaposition, constant solar energy within sight of ancient frozen water, makes those mountains some of the most valuable real estate in the inner solar system for future human exploration. Solar panels for power, ice for water and fuel, access to billion-year-old samples that could rewrite our understanding of early solar system history. The next generation of robotic missions is heading toward exactly this region. Some of them may be landing before this decade is over. What would it actually mean to establish a permanent human presence on the Moon? The comparison everyone reaches for is Antarctica. The research stations at the South Pole are operated by multiple nations, staffed year-round, and dedicated to science that can only be done in that extreme environment. No single nation owns Antarctica. The Antarctic Treaty of 1959 set aside the continent for peaceful scientific purposes and prohibited military activity and territorial claims. The stations there are proof that human beings can sustain themselves in an environment that is deeply hostile to human life, with no breathable air outside the buildings, temperatures that kill exposed skin in minutes, and months of complete darkness every year. The Moon is harder than Antarctica in almost every way. The lack of any atmosphere at all means that the risks from solar and cosmic radiation are severe. The temperature swings between lunar day and lunar night, which each last about 2 Earth weeks, are extreme enough to shatter unprotected materials. Abrasive lunar dust, electrostatically charged, and with a chemical composition that is mildly toxic and potentially harmful to lung tissue, would be a constant challenge for equipment and human health. And the psychological isolation would be different in kind from Antarctica, because even at the South Pole, you are still standing on a planet with weather and wind and the smell of cold air. The Moon offers nothing of that, and yet, human beings have built pressurized habitats in every extreme environment on Earth. We have spent years at a time on the International Space Station, dealing with weightlessness, radiation, and the profound psychological challenge of being enclosed in a small space with the same small group of people. We understand how to grow food in controlled environments. We understand how to recycle water. We know how to manage radiation exposure. The specific challenges of the Moon are different from anything we have faced before, but they are not categorically impossible. The more interesting question might be why? Why go back? What does a permanent human presence on the Moon accomplish that cannot be accomplished with robots? The answers are multiple, and not all of them are scientific. Scientifically, the Moon is an irreplaceable resource. Those Antarctic-style research stations on the lunar surface could house astronomers building radio telescopes on the far side, where Earth's electromagnetic noise is completely absent. A radio telescope on the far side of the Moon could observe the universe at frequencies and with sensitivity that are simply impossible from Earth's surface. It could potentially detect signals from the epoch just after the Big Bang before the first stars formed, reading the structure of the early universe from radio emissions frozen into the cosmic microwave background. The lunar poles could host observatories looking at the outer solar system and deep space from a stable platform with no atmospheric distortion and no weather. Geological surveys of the ancient highland crust could reveal the timeline of the late heavy bombardment, a period roughly 4 billion years ago, when the inner solar system was peppered with impactors in an intensity that may have sterilized early Earth repeatedly. Understanding that bombardment tells us about the conditions for life's emergence and survival. Economically, the Moon may hold concentrations of rare materials worth extracting. Helium-3, a relatively rare isotope on Earth, but potentially abundant in the lunar regolith after billions of years of solar wind implantation, is a proposed fuel for fusion reactors. If fusion energy ever becomes commercially viable, the Moon could theoretically supply enough helium-3 to power human civilization for millennia. The speculative nature of that future has not stopped serious economic analysis from being done. And then there is the argument that goes beyond science and economics entirely. The argument that is harder to make in a policy document but easier to feel on a clear night when you look up and see that white light hanging above the horizon. The Moon is the gateway to everywhere else. A permanent human presence on the Moon would make deep space exploration dramatically more feasible. Launching from the Moon requires far less energy than launching from Earth's deep gravity well. Fuel produced from lunar ice could be stored at orbital depots, making missions to Mars, the asteroid belt, and the outer solar system cheaper and more accessible. The Moon is not just a destination. It is the first step on the longest road in human history. Every Apollo astronaut who flew to the Moon and came back reported a version of the same thing. The Moon changed how they saw Earth. The overview effect. But many of them also said something else. They came back with an almost urgent conviction that humanity needed to leave. Not because Earth is broken or bad, because containment is fragile, because any civilization that exists on only one world is one catastrophic event away from extinction. Because spreading beyond our origin point is not ambition or restlessness, it is survival. The moon is the first credible step toward that. There is something worth saying here about what this decade feels like in the context of that longer arc. The generation that watched Apollo unfold on grainy television is aging. Many of them are gone. For the generation that came after, the moon was something that had already been done, a historical achievement filed away with other historical achievements, not a living frontier but a settled fact. Humans walked on the moon, and then we moved on. That perception is changing. The moon is a living frontier again, not just in the aspirational language of space agency press releases, but in the concrete reality of hardware being built, budgets being allocated, international agreements being negotiated over what exactly will happen when multiple nations establish a presence in the same region near the lunar South Pole. This is genuinely new. The legal and political framework for sustained lunar activity does not yet exist in finished form. The Artemis Accords, which multiple nations have signed, establish some principles for behavior on the moon, transparency about activities, protection of historic sites, including the Apollo landing zones, bilateral agreements for resource extraction, but they are not a treaty. They are not binding in the way international law typically requires. The rules of the road for the lunar South Pole are still being written. That is remarkable. We are living at the moment when the governance of another world is an active, unresolved political question. The decisions being made right now about who can go where on the moon, what can be extracted, how historical sites are protected and how disputes are resolved will shape the development of the moon for centuries. And above all of that, above the politics and the engineering and the economics, the moon itself is completely indifferent. It has been doing what it does for 4.5 billion years. Tonight it is reflecting the light of the sun back toward the Mayflowers and the people standing in their front yards with their phones out, trying to capture that golden rising disk before it climbs too high and turns too white for the photograph to look the way they remember the moon looking. We should talk about why the moon looks so different when it is near the horizon versus when it is high overhead, because the answer is not what most people expect. The moon appears larger near the horizon. It looks sometimes dramatically, almost absurdly large when it first rises, particularly when there are buildings or trees or mountains silhouetted against it in the foreground. As it climbs higher, it seems to shrink. By the time it is overhead, it looks modest, almost ordinary. This is an illusion. A precise, well-documented, thoroughly studied visual illusion, but an illusion. The angular diameter of the moon does not change meaningfully as it rises. You can verify this with a basic measurement. Hold a finger up to the rising moon, and then hold the same finger up to the high moon a few hours later. The size is the same. Your finger covers the same fraction of the disk both times. What changes is context. When the moon is near the horizon, your visual system has references to compare it to. Trees, buildings, the curvature of the landscape. Your brain interprets the moon as being near those objects, and its usual depth processing machinery concludes that something appearing so large while being so close must be genuinely enormous. When the moon is overhead, those references vanish. There is nothing to compare it to except empty sky, and your brain has no context for judging its size, so it appears smaller by default. The moon illusion has been studied extensively, and there is still some debate about the precise mechanisms. But it has been described at least as far back as Aristotle, which tells you something about how consistently it surprises human perception across cultures and centuries. There is a way to break the illusion deliberately. Turn around so your back is to the moon. Bend over and look at it between your legs, upside down. Without the visual context of the horizon and the familiar landscape, the moon suddenly snaps back to its true apparent size. It looks smaller, ordinary, not the swollen golden thing it appeared to be at the right side up. This is mildly disorienting the first time you do it. The moon does not look like what you just saw a moment ago. It looks like a different object. Same angle, same light, different context. Your brain is telling you two completely different things about the same photons. What the moon illusion illustrates is something deeper about how perception works. You are never experiencing raw reality directly. You're experiencing a model of reality assembled by a brain that is constantly making inferences, filling in gaps and using context to generate interpretations. The moon that feels enormous on the horizon is a construction. So is the moon that feels smaller overhead. Neither is more true than the other. Both are outputs from the same perceptual machinery that evolved to help you navigate a world where recognizing genuine size differences at different distances was a matter of life and death. The moon is a wonderful object for catching perception in the act. For a brief moment, with your back to it and your head between your knees on a cool May evening, you can feel your brain doing something it does constantly and visibly without your permission. Now let us spend some time on something that does not get enough attention in conversations about the moon, which is what the moon has meant to human beings across time and culture. Not the science, not the exploration. The other thing, the thing that lives in mythology and poetry and ritual and the parts of human experience that resist measurement. Go back far enough and the moon is everywhere. In every literate civilization we can trace, and almost certainly in those that predate literacy, the moon was a central, organizing presence in human life. This is partly practical. Before artificial light, the full moon provided the only reliable source of nighttime illumination strong enough to work by, to travel by, to hold large gatherings. Full moon nights were occasions for activity that was impossible in darkness. The rhythm of the lunar cycle, those 29.5 days from full to full, was one of the earliest human timekeeping frameworks. The word month is derived from the word moon. The two concepts are linguistically inseparable in most Indo-European languages, because they were conceptually inseparable in the cultures that developed those languages. A month was a moon. Time was counted in moons. Women's menstrual cycles were observed to roughly match the lunar period, an observation so striking that it generated mythological connections between the moon and femininity, fertility, and cyclical time that appear independently in cultures that had no contact with each other. The Babylonians developed a sophisticated lunar calendar nearly 4,000 years ago that was accurate enough to predict eclipses. They track the moon not as a mystical object, but as a precise instrument, a clock in the sky. Their observations were systematic, recorded on clay tablets, passed down through generations of professional astronomers who sat on the rooftops of temples and documented what they saw with a rigour that would not look out of place in a modern observatory. Chinese astronomers maintained continuous lunar records stretching back thousands of years. The traditional Chinese calendar is lunisolar, adjusting the lunar months against the solar year by inserting an extra month periodically, a technique called intercalation that was developed independently in multiple cultures because it is the only way to keep a lunar calendar synchronized with the seasons over the long term. The Islamic calendar remains a purely lunar calendar, making no adjustment for the solar year. This means that Islamic holy months, including Ramadan, cycle through all seasons over the course of about 33 years. The beginning of each lunar month is traditionally determined by the first visible crescent of the new moon, observed by a human witness. This is not an astronomical calculation. It is an act of looking. There are trained moonsighters in Muslim communities around the world who watch for that first thin crescent every month, and when they see it, they report it, and the month begins. The deliberate preservation of that human element, the actual act of watching and witnessing, in the determination of sacred time is something I find remarkable. In an era when we can calculate the position of the moon to the nearest centimetre at any moment in the next 10,000 years, the decision to maintain the practice of looking seems like a statement about what matters. Not the calculation, the act of attention. The full moon in Buddhist tradition is the time of Uposatha, a day of intensified practice and reflection, observed by monks and laypeople across the Buddhist world. Many significant events in the life of the Buddha are associated with full moon days, his birth, his enlightenment, his first teaching, his death. Whether these associations are historical or symbolic, they encode the same intuition that appears in culture after culture. The full moon is a time for significance, a natural interval marker that invites reflection on what has passed and what is coming. The Hebrew calendar, like the Chinese, is lunisolar, and the full moon is significant in the timing of major festivals. Passover begins on the 15th of the Hebrew month of Nisan, which is by definition the full moon of that month. Easter, in the Christian tradition, derived from Passover, follows a related lunar calculation, the first Sunday after the first full moon, after the spring equinox. The moon determines the date of the most important festival in the Christian calendar, even though most Christians have no idea that is the case. The Easter egg hunt in April happens on a day calculated from the moon's position. You could spend a lifetime following these threads. The moon is embedded in the timing of human religious and agricultural life in ways so ancient and so pervasive that they have largely become invisible. They are the background of the calendar rather than its foreground. We celebrate festivals on dates whose lunar origins we have forgotten, observe holidays whose timing was calculated by people who watched the moon from rooftops millennia ago. During totality, when the moon blocks the photosphere completely, the sky around the sun darkens enough that the corona blazes into visibility. It appears as a white halo with complex structure, streamers and loops and filaments extending outward in patterns shaped by the sun's magnetic field. No photograph fully captures what observers describe when they see it for the first time. The dynamic range of human vision in that moment appears to exceed what cameras can currently reproduce. The corona is one of the great unsolved problems in solar physics. The photosphere, the surface you cannot safely look at directly, has a temperature of around 5,500 degrees Celsius. The corona, which is the outermost atmosphere above it, has a temperature of somewhere between 1 million and 3 million degrees. This is deeply counterintuitive. If you move away from a heat source, you expect things to get cooler, not hotter. The fact that the sun's atmosphere gets dramatically hotter as you move away from its surface is a problem that has occupied physicists for decades and is still not fully resolved. Several mechanisms have been proposed. One involves Alfvén waves, a type of wave that propagates along magnetic field lines and can carry energy outward from the surface. Another involves nanoflares, tiny magnetic reconnection events happening constantly across the sun's surface that release bursts of energy too small to detect individually but significant in aggregate. The current best answer is probably some combination of mechanisms, but the corona continues to surprise researchers. Total solar eclipses were essentially the only tool astronomers had for studying the corona for most of scientific history. The invention of the coronagraph, a device that artificially blocks the sun's disk inside a telescope, helped, but ground-based coronagraphs have to contend with scattered light in the atmosphere that total eclipse observers do not. Space-based coronagraphs like those on the SOHO satellite have opened up continuous corona observation, but they typically have to block a region larger than the solar disk itself, obscuring the inner corona. The total eclipse still provides something that instruments have struggled to replicate. This is another version of the same theme that keeps recurring when we talk about the moon. Its presence in our sky is not just poetic, it creates conditions that would not otherwise exist. The study of the corona, which is directly relevant to our understanding of space weather and solar activity that affects satellites and power grids and communications on Earth, was advanced for centuries specifically because the moon is the size it is and sits at the distance it does. Space weather is worth pausing on, because it is one of those topics that sounds technical and abstract until it becomes very concrete very quickly. The sun is not a stable object. It is a dynamic, churning, magnetically complex star that constantly emits a stream of charged particles called the solar wind, and periodically releases much larger bursts of energy and matter in events called coronal mass ejections and solar flares. The scale of these events varies enormously. Small ones happen constantly. Large ones happen on cycles loosely tied to the sun's roughly 11-year activity cycle, which is currently approaching a solar maximum, meaning we are in a period of elevated activity. The most significant space weather events are classified as X-class solar flares, the most powerful category, and the coronal mass ejections that sometimes accompany them. When a large coronal mass ejection is directed at Earth, a stream of magnetized plasma traveling at millions of kilometers per hour arrives at Earth within 1 to 3 days. Earth's magnetic field deflects most of it, producing geomagnetic storms whose visible signature is the aurora. But strong enough events can induce electrical currents in long conductors on the surface, including power lines and pipelines, and can damage or disable satellites. The largest geomagnetic storm in recorded history was the Carrington event of 1859. Telegraph systems across Europe and North America failed. Some telegraph operators reported receiving shocks. Aurora were visible at latitudes as far south as Cuba and Hawaii. If an event of equivalent magnitude struck today, the damage to electrical infrastructure and satellites could be severe enough to cause cascading failures across interconnected systems. Estimates of the cost range widely, but serious analyses put the upper range in the trillions of dollars. A significant event, smaller than Carrington but still historically notable, occurred in May of 2024. Aurora were visible across unusually low latitudes around the world, reaching parts of the United States, Europe and Asia that rarely see them. It was a reminder that space weather is not a historical curiosity, but an ongoing phenomenon that the modern world has not fully reckoned with. The far side of the moon comes back into relevance here. One of the limitations of space weather forecasting is that we cannot see what is happening on the far side of the Sun, which means coronal mass ejections from that region can arrive with little warning. A monitoring station at the right orbital position, or eventually instruments on the lunar far side, could contribute to the global space weather monitoring network in ways that would improve warning times. Everything connects: the moon's distance, the moon's size, the moon's locked face, the moon's gravitational history, the moon's position as a potential platform for instruments that do not fit anywhere else in the inner solar system. The object hanging in the sky tonight is not just a light for the night, or a tide maker, or a calendar, or a destination. It is a presence that has shaped what we can know and how we can know it. Let us talk about where we are in the long arc of the moon's story. The moon is currently moving away from Earth at a rate of about 3.8 centimeters per year. This rate has varied over geological time. It is faster now than the long-term average, but the direction is consistent. Earth's tidal bulge, raised by the moon, always sits slightly ahead of the moon in its orbit because Earth rotates faster than the moon orbits. The moon's gravity pulls on that bulge and slows Earth's rotation. Earth's gravity pulls on the moon's position and accelerates it slightly. Conservation of angular momentum means the energy going into slowing Earth's rotation has to go somewhere, and it goes into raising the moon's orbit. When Earth and Moon formed, the moon was much closer. Days were much shorter. The tides were much higher. Over 4.5 billion years, the moon has receded to its current distance, and Earth's day has lengthened from perhaps 6 hours to 24. In the far future, this process will continue until Earth's rotation slows to the point where it is tidally locked to the moon, just as the moon is tidally locked to Earth. At that point, both worlds will keep the same face toward each other permanently, and the tidal breaking will stop. The day and the month will be the same length, somewhere around 47 of our current days. This is not relevant on any human timescale. It will not happen for billions of years, longer than the current age of the solar system. By the time it would happen, the sun will have changed dramatically, and the question of whether Earth and Moon still exist in their current forms is genuinely uncertain. But the process is happening now. The tides slowing Earth's rotation are the same tides that you can observe on any coastline today. The seconds being gradually added to Earth's day are real. We are inside this process, moving through it. During totality, when the moon blocks the photosphere exactly, the corona suddenly appears. It blazes out from behind the dark disk of the moon in streamers and plumes of white light, symmetrical or asymmetric depending on where we are in the solar cycle, sometimes forming a perfect halo, sometimes stretched into long tendrils along the sun's magnetic field lines. It is, by every account of everyone who has ever seen it, one of the most extraordinary visual experiences available to a human being on the surface of this planet. The temperature of the corona is a scientific mystery that took decades to properly formulate and is still not fully solved. The solar surface temperature is roughly 5,500 degrees Celsius. The corona is millions of degrees hotter. This makes no sense from the obvious physics. Heat should flow outward from a hot source, not inward. The surface should be hotter than the atmosphere above it, the way a campfire is hotter than the air above it. But the corona is hotter by a factor of hundreds. Something is carrying energy from the interior of the sun outward through the photosphere and depositing it in the corona in massive quantities. The leading candidates involve waves moving through the solar magnetic field, a process called wave heating, and small explosive events called nanoflares, microscale magnetic reconnection events that each release modest amounts of energy but occur at such overwhelming frequency across the sun's entire surface that their cumulative effect heats the corona to those extreme temperatures. Total solar eclipses were crucial in developing our understanding of this problem. The first observation of helium in the sun came from spectroscopy during a total eclipse in 1868, years before helium was discovered on Earth. The element was named after Helios, the Greek sun god, because it was found in the sun before it was found at home. Spectroscopic analysis of the corona during eclipses led to the discovery of coronal material that seemed to contain an unknown element, which astronomers called coronium, and which turned out to be ordinary iron at such extreme temperatures that its electrons were stripped away in ways that altered its spectral signature beyond easy recognition. The Moon, by its precise size and distance, has acted as a natural scientific instrument for centuries. By blocking the Sun, it revealed what was behind the Sun's glare. By its predictable motions, it allowed the development of lunar calendars and navigation tables. By its tidal effects, it shaped the conditions for life. And by its eventual disappearance from the sky as it continues to drift away, it will end the era of total eclipses and close a chapter in natural history that has lasted billions of years. We mentioned that we are living in the window when total eclipses are possible. That window is finite. The Moon moves away at roughly 3.5 centimeters per year, a rate that will have it visibly smaller in the sky in tens of millions of years, finally too small to fully cover the Sun in hundreds of millions of years. After that point, only annular eclipses will be possible. The Moon's smaller disk surrounded by the Sun's ring of fire, the corona never fully revealed. The fact that we are alive during the window of total eclipses, that the coincidence of apparent sizes that makes them possible, exists right now, in the same geological instant when human beings developed the technology and scientific understanding to appreciate what they are witnessing, is one of those facts about our situation that is genuinely hard to process. It might be a coincidence, pure, indifferent chance. The universe is large enough that somewhere in it, some species must be living through exactly this coincidence, and here we are. Or it might be that the same conditions that produced creatures capable of appreciating total eclipses also required the Moon to be at the distance it is, because that distance was necessary for the tidal and gravitational stability that complex life required, and so the window of eclipses and the existence of observers capable of noticing it are not independent events. Either way, we are here, and the window is open, and the next total solar eclipse visible from North America will cross the continent again in 2033 if you are on the right path in the right part of the country. The flower moon will not be that, but the same moon that is rising tonight will be there. There is a particular quality of light on a landscape illuminated by a full moon that is unlike any other light in our experience. Photographers and painters, and anyone who has stayed up late enough to walk outside on a clear full moon night knows what I am describing. It is bright enough to navigate by, to distinguish shapes, to cast shadows. Fence posts cast moon shadows on damp grass. Clouds glow silver-white from behind. The surface of water reflects a column of light toward you wherever you are standing. But the colour is wrong, or rather, different. The light is white and cool, and it washes the colour out of things in a way that sunlight does not. Colours that are vivid in daylight become muted, greyish, soft. Objects that have clear, distinct colours during the day merge together in monochrome. The world takes on a quality of old photographs. This is partly because of the way the moon reflects sunlight. The lunar surface reflects only about 12% of the sunlight that hits it, making it surprisingly dark as astronomical bodies go. What it does reflect is light shifted slightly from the colour spectrum of raw sunlight by the mineralogy of the lunar surface. But the dominant reason the moonlit world looks different is simpler. The intensity is low enough that our eyes shift from cone vision to rod vision, and rod cells do not distinguish colour. In moonlight, we are seeing with the part of our visual system that evolution optimised for motion detection in low light, not the part optimised for colour discrimination. The moon strips the colour from the world not by changing the light, but by changing which part of your eye is doing the work. Ancient hunters operating by moonlight were using a visual system tuned for exactly this. Movement against a pale background. Contrast rather than hue. The moonlit landscape is the landscape our deep ancestors hunted in, navigated in, watched for predators in. There is something in the human nervous system that responds to moonlight in a particular way, not just aesthetically, but perhaps something older than aesthetics. Let us think for a moment about the other planets with their moons, because the variety in the solar system turns out to be remarkable, and comparing what we have to what exists elsewhere puts the moon in sharper relief. Mars has 2 small moons, as we mentioned, Phobos and Deimos. They are named after the sons of Ares, the Greek equivalent of Mars, meaning fear and dread. They are tiny, irregular. Phobos, the larger one, is only about 27 kilometers across at its widest. From the surface of Mars, Phobos would appear as a bright point of light moving rapidly across the sky, crossing from horizon to horizon in about 4 hours and setting in the west despite rising in the east. It orbits so close to Mars that it moves faster than Mars rotates, pulling ahead of the planet's spin. Phobos is also spiraling inward. Unlike our Moon, which is moving away from Earth, Phobos is gradually falling toward Mars. Within about 30 to 50 million years, it will cross the Roche limit, the distance at which Mars's tidal forces will tear it apart, and it will either impact Mars or disintegrate into a thin ring. Mars will briefly have a ring system, then nothing. From the surface of Mars, if any life exists there to observe it, the spectacle of Phobos breaking apart over millions of years would be an extraordinary event. The sky would change. What had been a moving point of light would become a spreading arc of debris, a temporary ring glowing in the Martian night. And then, as the fragments spiral down through the Martian atmosphere, a long, slow bombardment of the surface from the material of their moon. Nothing like this is visible from Earth in any timescale relevant to human experience. But it is happening. Right now, Phobos is about 6 meters closer to Mars than it was a century ago. The change is immeasurably slow on any human scale, but it is real, and it is inexorable. Jupiter presents a completely different picture. Jupiter has 4 large moons, discovered by Galileo in 1610, each one a world of genuine complexity and interest. The innermost of those large moons is a place of extraordinary violence. It is the most volcanically active body in the solar system, covered in lakes of molten sulfur, erupting continuously with plumes that can reach hundreds of kilometers into space. The cause is tidal heating. Jupiter is so massive and so close that its gravity flexes this moon's interior continuously, generating enormous amounts of heat through friction. The moon is being kneaded by Jupiter's gravity like dough being worked by invisible hands. The second large moon of Jupiter is among the most intriguing objects in the solar system. Beneath its cracked and ridged ice surface lies a global ocean of liquid water. Not possible liquid water, confirmed liquid water, detected by magnetic field measurements from the Galileo spacecraft in the 1990s. The ice shell above that ocean is estimated to be somewhere between a few kilometers and tens of kilometers thick, and beneath it, in contact with rock on the bottom, is an ocean that may be twice the volume of all of Earth's oceans combined. This matters enormously for the question of whether life exists elsewhere in the solar system. Life on Earth began in the ocean. The energy sources available at the bottom of that Jovian moon's ocean, hydrothermal vents heated by tidal flexing, provide the same basic chemistry that hydrothermal vents on Earth's ocean floor support today. Complex ecosystems of life exist on Earth at hydrothermal vents without any energy input from sunlight. The possibility that something similar exists in that icy moon's hidden ocean cannot be dismissed. It is, in fact, one of the most scientifically serious possibilities for extraterrestrial life in the solar system. Future missions are being designed to explore that ocean. A spacecraft is currently en route to the Jovian system, a joint mission by the European Space Agency that will make multiple close flybys of that icy moon and 2 of its siblings over the coming decade. A NASA mission will follow, designed specifically to characterize the ice shell and eventually drop a probe through it. If there is life in the solar system beyond Earth, that moon of Jupiter is one of the best candidates for where to find it. And the moon we are looking at tonight is, in a sense, the reason we will be able to go look. The infrastructure being built for lunar exploration, the launch systems, the deep space navigation, the life support, the long-duration mission experience is the foundation on which those future missions to the outer solar system will be built. Saturn has its own extraordinary moon in Titan, the only moon in the solar system with a thick atmosphere. Titan's atmosphere is denser than Earth's at the surface. It is made primarily of nitrogen, as Earth's is, with the second most abundant component being methane rather than oxygen. At Titan's extreme cold, methane plays the role that water plays on Earth. It evaporates, it forms clouds, it rains, it flows in rivers and lakes across the surface. There are methane lakes near Titan's North Pole that are as large as some of the Great Lakes. The Cassini spacecraft, which spent 13 years orbiting Saturn and making repeated close flybys of Titan, revealed a world of staggering variety. Sand dunes of organic material stretching hundreds of kilometers, river valleys carved by methane floods, a subsurface ocean of liquid water beneath Titan's ice crust, similar to what exists at that Jovian moon, raising the same questions about habitability. We have a lander heading to Titan. Dragonfly, a rotorcraft lander, is designed to fly through Titan's thick atmosphere, moving from location to location like a helicopter, and is targeted to arrive in the mid-2030s. It will land in a region of complex organic chemistry and look for the signatures of prebiotic chemistry, the chemical processes that preceded life on Earth, but have never been observed happening elsewhere. None of this is science fiction. These missions exist. The hardware is being built or has been built. The science is being planned. Within the lifetimes of many people watching tonight's flower moon, we will have sent robotic explorers to the most promising habitable environments in the solar system and looked directly for the chemistry of life. The moon that is rising tonight is the point of departure for all of that, literally and figuratively. Let us think about something that does not get enough attention in popular discussions of space. The question of scale, not the scale of the solar system, which is familiar territory in broad strokes, but the scale within that familiarity, the distances and times involved in what we have been discussing. The moon is about 384,000 kilometers away from Earth. That number is abstract until you try to make it concrete. If you drove a car at a constant highway speed without stopping, you would reach the moon in roughly 5 months. The Apollo astronauts, traveling at speeds far exceeding any car, took about 3 days each way. The Sun is about 390 times farther away than the Moon. Light takes about 8 minutes to travel from the Sun to Earth. The Sun is not very far away, cosmically speaking. It is our local star, and even our local star is at a distance that renders most human intuitions useless. The nearest other star is just over 4 light-years away. The light you are seeing from it tonight, if you can find it in the sky, left that star 4 years ago. In that 4 years, civilizations have risen and fallen, technologies have been invented and made obsolete, lives have been lived from beginning to end, and the light that shows you that star tonight departed before any of it. The Milky Way is roughly 100,000 light-years across. The light from the most distant stars in our own galaxy that you can see tonight left those stars before modern humans existed, before written language, before agriculture, before Stonehenge or the pyramids or any other structure our species has built. The star whose light is reaching your eye tonight has been shining all of recorded human history and most of the time before it, and the light crossing that distance is only now arriving. The observable universe is about 93 billion light-years across. The most distant galaxies we can observe with our best telescopes are so far away that the universe was only a few 100 million years old when their light left them. The universe is now about 13.5 billion years old. We are looking back through almost all of its history with every deep observation, and sitting in the middle of all of this, a third of the way out from the center of an unremarkable spiral galaxy, orbiting an average star, is a small rocky planet with a moderately large companion moon. The moon that is rising tonight is not large by cosmic standards, not significant by cosmic standards. It is a piece of rock and ice and ancient volcanic ash, 3,470 kilometers across, formed in violence and drifting slowly away, but tonight it is above your head. Tonight it is the flower moon, and you are the part of the universe that is aware of all of this looking up. There is a version of the universe in which no part of it is aware of itself, in which stars explode and galaxies collide and black holes consume, and everything happens in a silence so total and so complete that the word silence is not even applicable because there is no contrast, nothing it could be contrasted with. That version of the universe may be the majority of the universe, the fraction that has achieved enough complexity to observe itself, to wonder about its own nature, to look up at a full moon on a May evening and understand what it is looking at. That fraction may be vanishingly small. We are in it. There is nothing inherently comforting about that, and there is nothing inherently troubling about it either. It is just a fact, a remarkable fact that repays attention. Let us come back to the moon with all of that in mind. The surface that you're looking at tonight has not changed substantially in 1 billion years. The major volcanic events that created the Maria ended long ago. The bombardment that shaped the highlands peaked billions of years ago and has slowed to a trickle. The moon is not geologically dead. There is evidence of very recent outgassing from its interior in a few locations, but it is geologically quiet. The face you see tonight is essentially the face that hominids and pre-hominids saw when they looked up before the genus Homo existed, before the first stone tools were made, before the migration out of Africa, before all of it. The individual craters that dot the surface have accumulated slowly over that time, 1 or 2 large impact events per million years, on average, with occasional larger events punctuating the quieter periods. Some of the craters visible tonight with the naked eye are the results of impacts that happened within the last few 100 million years, geologically recent events. Others are scars from 4 billion years ago, from the period of heavy bombardment when the inner solar system was still clearing out the debris of planetary formation. Looking at the moon is a form of time travel that requires no technology beyond your eyes. The patterns of light and dark that you see are not changed from what early modern humans saw 200,000 years ago. The same sea of tranquility, the same ocean of storms, the same bright ray system spreading from the crater, Tycho near the southern highlands. The moon your ancestors knew is the moon you are looking at. Tycho is worth mentioning specifically. It is one of the most prominent features on the full moon, a bright circular crater near the south of the near side, with a ray system that in good lighting appears to extend nearly across the entire face of the moon. The rays are formed from material ejected during the impact that created the crater, lighter material that landed on the darker volcanic plains and has not yet had time to darken through exposure to the solar wind and cosmic radiation. Tycho is geologically young. In lunar terms, young means less than 100 million years old. There were dinosaurs on Earth when the impactor that created Tycho struck the moon. The non-avian dinosaurs had not yet gone extinct when that bright splash of ejecta spread across the lunar surface. The moon you see tonight, those bright rays streaming from that southern crater, is a record of an event that happened while a certain famous mass extinction had not yet occurred. The continuity of the moon's face across geological time becomes even more pointed when you think about it from the other direction. The moon has been looking at Earth while Earth changed in ways almost unimaginable from our current vantage point. It watched the supercontinent Pangaea assemble and then break apart. It watched the mass extinctions and the radiations that followed. It watched the ice ages advance and retreat. It watched the first fish climb onto land, the first reptile, the first mammal. And then, in the last moment before midnight on the cosmic clock, it watched a particular species of upright ape develop language and fire and agriculture and writing and cities and telescopes, and eventually, after millions of years of looking up, reach out and actually touch it. That reaching out happened, in historical terms, last week. The Apollo program's most recent mission was in 1972. The oldest surviving Apollo astronaut was born when the airplane was still a recent invention, when the idea that a human being would walk on the moon in their lifetime was science fiction, and then they lived to do exactly that, and then watched the world move on while they aged. The history contained in the lifespan of the people who walked on the moon is extraordinary. Born before commercial aviation was common, dead in a world where AI can write poetry. And in between, they walked on another world. The light reaching your eyes from the moon tonight is already about 1¼ seconds old when it arrives. It left the moon 1¼ seconds ago, travelling at the speed of light, covering 384,000 kilometres in the time it takes you to blink. By the time it hits your retina and your visual cortex processes it into the image of a full moon, the event that produced that image has been over for more than a second. This is trivial compared to the time delays involved in observing distant objects. But it is not nothing. You're seeing the moon as it was, not as it is. The moon exists in a genuine, physical sense in your slight past. Everything you observe is slightly historical. The sun you see is 8 minutes historical. The nearest star is 4 years historical. The most distant visible galaxy is billions of years historical. Observation is always archaeology. Looking outward is always looking backward. The universe presents itself to us not as a live feed, but as a layered archive. Each distance a different epoch, each photon a message from a specific moment in time. This is one of the stranger things about being a conscious observer in the universe. You're always looking at the past. Even the person standing across the room from you is being seen as they were a tiny fraction of a second ago. The delay is imperceptible. The reality is absolute. The moon in your sky tonight is the moon as it was 1¼ seconds ago. You will never see the moon as it is at this precise moment, because by the time the light from that moment reaches you, the moment is over. The present moon is inaccessible to you. All you can have is the travelling light of its immediate past. There is a philosophical tradition that finds this kind of fact disturbing, evidence of a barrier between the observer and the observed, a reminder that direct access to reality is always mediated. And there is another tradition that finds it wonderful, evidence of the physical reality of time, of the way space and time are inseparable, of the fact that what seems like mere distance is actually a journey through the fourth dimension. The moon is not just far away in space, it is slightly behind us in time. We have been talking through all of this mostly about the moon as an object, what it is made of, how it formed, how it moves, what happens on its surface. Let us spend some time now on what the moon has done to human beings as observers, as thinkers, as scientists. The moon is where humanity learned to do planetary science. Long before spacecraft, the moon was a laboratory for observational astronomy. Galileo turned his first telescope toward the moon in 1609 and saw, to his astonishment, not the perfectly smooth celestial sphere that Aristotelian doctrine insisted all heavenly bodies must be, but a rugged, mountainous, cratered landscape. He measured the heights of lunar mountains by observing how their peaks caught sunlight while their bases were still in shadow, using geometry to calculate what must be a mountain at least 4 kilometers high. He did this with a handmade telescope and mathematics, and he was right. The moon provided the evidence that punctured the ancient view of a perfect, unchanging heavenly realm, distinct in nature from the imperfect, changeable Earth. The heavens were not perfect. They were rocky and cratered and rough, just like the Earth, which was itself a heavenly body if you were standing on the moon looking back. The distinction between celestial perfection and terrestrial imperfection collapsed once you could see the moon's surface clearly. It took time, decades, for the intellectual implications to fully ripple through. But the moon started it. Isaac Newton worked out the mathematics of universal gravitation partly by checking his equations against the moon. The insight that the same force that made an apple fall from a tree also governed the orbit of the moon around Earth was, in Newton's own account, one of the key moments in developing the theory. If gravity extended from Earth's surface to the moon, then it was not a local effect but a universal one. The universality of physical law, the idea that the same equations govern everything from falling apples to orbiting moons to the motions of distant planets, is one of the central and most productive ideas in the history of science. The moon helped establish it. In the 19th century, the study of the moon's motion, its precise orbital mechanics, was among the most demanding problems in applied mathematics. The moon does not follow a perfectly elliptical orbit. Earth's gravity is the dominant force, but the Sun and Jupiter and the other planets all exert small perturbations, and those perturbations accumulate in complicated ways. The mathematics required to predict the moon's position accurately enough for navigation purposes occupied some of the finest mathematical minds of the century. The Nautical Almanac, published by the British government and used by navigators around the world to determine longitude at sea using lunar observations, was a product of that mathematics. The moon effectively powered global navigation for centuries. The development of accurate lunar tables required new mathematical techniques. Those techniques, developed to solve the moon problem, turned out to be applicable in other domains. The mathematics of small perturbations, the methods for handling problems where many forces are acting simultaneously at different scales, found applications in celestial mechanics, in electromagnetic theory, in quantum mechanics. A problem that seemed narrow and specific, predicting exactly where the moon would be in the sky on a given night, turned out to require mathematics of broad applicability. This is a pattern that appears repeatedly in the history of science. A practical problem forces the development of a new tool, and the tool turns out to be more general than the problem that required it. The moon also gave us our first rigorous test of the theory of general relativity. Einstein published the general theory of relativity in 1915. The theory made several predictions that differed from Newtonian gravity in specific measurable ways. One prediction concerned the precession of the perihelion of Mercury's orbit, a tiny discrepancy that had been observed but not explained. Relativity explained it. Another prediction concerned the bending of light around massive objects, confirmed during a total solar eclipse in 1919. But there was a subtler test available using the moon, and it became one of the most precise tests in all of physics. Reflectors left on the lunar surface by Apollo missions are still there. By firing laser pulses from Earth at those reflectors and timing how long the pulses take to return, scientists have been measuring the precise distance to the Moon for decades, to within millimeters. This measurement tests something called the equivalence principle, the idea that gravitational mass and inertial mass are exactly equal for all objects regardless of their composition, which is a foundation of general relativity. The Earth and the Moon are made of different materials, have different compositions. If the equivalence principle holds exactly, they should fall toward the Sun at exactly the same rate despite those differences. If they fell at even slightly different rates, the Moon's orbit around Earth would show a tiny characteristic wobble called the Nordtvedt effect. Decades of laser-ranging data show no such wobble to any measurable degree. The equivalence principle holds to extraordinarily high precision. General relativity passes the test. Every time a laser pulse bounces off those Apollo retroreflectors, it is both confirming our best theory of gravity and connecting us, in a very literal physical sense, to the 12 people who walked on the Moon and left those reflectors behind. The Moon is still doing science, without leaving, without changing, simply by being there. There is a conversation worth having about language and the Moon that I have been saving for late in this discussion, because I think it is more interesting in context than it would have been at the beginning. The English word lunatic derives from the Latin luna, meaning moon. The belief that the Moon could affect human mental states, particularly inducing madness or erratic behaviour at the full moon, is ancient and cross-cultural. The Romans believed it. Medieval Europeans believed it. The association was strong enough to be embedded in language, and through language, to persist into the modern era. Does the full moon actually affect human behaviour? This is a question that has been studied seriously, and the answer is almost certainly no, not in any consistent, reproducible way. Analyses of emergency room admissions, violent incidents, psychiatric crises, and birth rates across large data sets have repeatedly failed to find a statistically significant correlation with lunar phase. The belief persists, probably partly because of confirmation bias. On a beautiful full moon night, people notice things that feel connected to it, and they remember those connections. On a dull quarter moon night, nothing seems connected to the Moon, and there is nothing to remember. The belief also persists because of the genuine demonstrable effects of the Moon on other biological systems, which makes it feel plausible that similar effects on human beings might exist, even if they have not been measured. Tidal effects on the ocean are real, the sleep research suggesting subtle influences on human sleep patterns, if confirmed by further work, would be real. The aggregation of genuine effects elsewhere, combined with our species' deep pattern-matching instinct, and the visceral impression that full moon nights feel different, produces a belief that turns out not to be supported by data. But here is the interesting thing about studying why a false belief persists. It tells you something true about the observers. The persistence of lunar madness beliefs tells you that human beings are exquisitely sensitive to atmosphere, that we are deeply attuned to light and the quality of nights, that we are creatures who notice when the world feels different, even when the difference is not mechanistically causal. The full moon night does feel different. The light is different. The shadows are different. The landscape looks different. Something in the experience of a full moon night does shift something in human perception. It is just not the Moon making you crazy. It is the Moon making the world beautiful and unusual, and human beings responding to that, and then reaching for the nearest available explanation. The nearest available explanation has been, for most of human history, some version of supernatural influence. The Moon controls the tides, the menstrual cycle, the planting season, the behaviour of animals, so why not also the moods of people? The logic is not unreasonable. It is just that the data, when we finally gathered it carefully, did not support that particular extension. Science has a tendency to narrow the range of things the Moon is directly responsible for. It does not cause madness. It probably does not significantly affect most of the biological rhythms we once attributed to it. The mechanisms that remain, tidal effects, axial stabilization, the long-term geological and evolutionary consequences, are enormous and real, but they are impersonal. They are physics, not magic. And yet the Moon is still up there tonight, still doing what it does, and people are still going outside to look at it, not because of the physics, but because of something older and harder to name, something in the beauty of the thing, something in the light it throws on the world, something in the way it has been there, visibly and reliably, across the entire span of human experience, a constant in a world of constant change. In the Romantic period, the moon became one of the central images of poetry and art, precisely because it represented the idea of something that could be felt, but not fully analysed, something that moved you without being entirely explicable. The moon in Shelley and Keats and Goethe was an emblem of emotion, melancholy, longing, the beautiful that is also transient. The full moon, particularly, because its fullness is brief. Tomorrow it will be slightly less full. The peak is already past. The beauty you are witnessing is already departing. There is a Japanese concept, mono no aware, that translates roughly as the pathos of things, the bittersweet awareness of impermanence. It is associated strongly with cherry blossoms, which bloom for only a brief period and are valued partly because they will fall. The beauty is connected to the brevity. Awareness of the ending makes the present more present. Mono no aware applies to the full moon in a way that I suspect the concept was designed for. The peak was this afternoon, at 13 minutes past 1. The moon that rises tonight is already falling away from that peak. By tomorrow it will be noticeably less full. By the end of the week it will be half. The flower moon of May 2026 is happening right now, and it will not come back. The next full moon will be a different full moon, in June, named for a different moment in the natural year. This particular convergence of geometry and season and calendar will not repeat. Every full moon is the last full moon of its kind. The universe is 13.5 billion years old. The moon is 4.5 billion years old. Human civilization is roughly 10,000 years old in any form we would recognize. A few thousand in any form we would be comfortable in. You have been alive for a few decades. The number of full moons you will see in a lifetime is somewhere around 1,000, perhaps a few hundred more if you are lucky. Tonight is one of them, 1,000 full moons across a lifetime. It sounds like a lot until you think about the fact that the moon has been full roughly 6 billion times since it formed. Your 1,000 is a fraction so small it is not meaningful to calculate, and yet your 1,000 is the only 1,000 that exists from where you are standing looking up. The stars above the moon tonight are old beyond the capacity of human comprehension. The light of the nearest ones has been travelling for years to reach you. The light of the farthest ones you can see has been travelling for thousands of years, before writing, before cities, before most of what we call history. That light was already in transit, aimed at this moment without knowing there would be a moment waiting for it. And here we are. The flower moon carries a name given by people who watched the world closely and found a way to hold time inside language. The mayflowers that give this moon its name are blooming right now, in whatever yard or field or park exists near you. The same warming that pulled them out of the ground is the same tilt of Earth's northern hemisphere toward the sun that tells you it is spring, that has been telling living things it is spring for hundreds of millions of years, long before there were flowers or moons or words for any of it. The geometry of the solar system is indifferent to all of this. The moon does not know it is full. The sun does not know it is providing the light. The Earth does not know it is May. The whole magnificent machine of orbits and tides and axial tilts and reflected light operates without awareness, without intent, without any concern for whether anyone is watching. But someone is watching. You are. And the fact that you are watching is, on any honest accounting, more improbable and more remarkable than anything we have been talking about. The formation of the moon from a catastrophic collision, the development of tidal locking, the chance alignment of apparent sizes that makes total eclipses possible, the stabilization of Earth's axial tilt that allowed complex life to develop, the origin of life in tidal pools energized by that same moon's gravity, the 4 billion years of evolution that produced a creature capable of understanding all of this, the particular sequence of events in the last 10,000 years that produced language and science, and a tradition of watching the sky with careful attention, and then the particular sequence in the last 67 years that produced the technology to send 12 human beings to the surface of the moon and bring them back, and the technology to measure the distance to the moon with millimeter precision from the retroreflectors they left behind, and the technology to plan a return, and the technology to transmit a voice into your ears on a May evening describing all of it. That chain is so long and so contingent that the word improbable is insufficient. The appropriate word is something like miraculous, if you strip the word of its supernatural connotations and leave only its original meaning, worthy of wonder. There is a tradition in astronomy of what is sometimes called the cosmic perspective, the deliberate practice of placing human affairs in the context of astronomical scales, of using the vastness of the universe as a way of reframing what seems important and what does not. The tradition has genuine value. The things that feel urgent and enormous in human life, political conflicts, personal setbacks, the anxieties of daily existence, do shrink when you hold them against the backdrop of a universe that is 93 billion light-years wide and 13.5 billion years old. But there is a version of the cosmic perspective that tips into nihilism, that uses the scale of the universe as an argument that nothing matters because nothing is significant in cosmic terms. And I want to push back against that because I think it misuses the perspective. The universe is not aware of itself except through observers like us. The improbability of our existence is not an argument for our insignificance. It is an argument for the opposite. We are the part of the universe that knows it is a universe. We are the part of the universe that can observe a full moon on a spring evening and understand what the light is doing and where it came from and what it means. That capacity is not diminished by the fact that the universe is large. It is made more remarkable by it. The flower moon is 4.5 billion years old. You're a few decades old. It outweighs you by a factor that makes the word incomprehensible necessary. It has been circling this planet since before anything remotely like life existed on Earth. And tonight it needs you to look at it. Not because the moon requires observation, not because looking at it has any effect on what the moon does, but because the looking is what makes the moon matter, in any sense beyond the purely physical. The beauty is not in the moon alone. The beauty is in the relationship between the moon and the mind that encounters it, and finds it beautiful. That relationship is what you are participating in when you go outside tonight, when you let your eyes adjust to the dark and find that rising disk above the tree line. This particular fullness peaked at 13 minutes past 1 this afternoon. It has been sliding back from that peak for hours, by fractions of a percent that no eye can detect and no photograph can capture. It will slide further through the night and through tomorrow and the day after. By the end of the week it will look like a clearly different phase, unmistakably waning. By the end of the month it will be new again, invisible, beginning the next cycle. The moon is not waiting for you. It has never waited for anything. It will be full whether you see it or not, and it will wane whether you mourn it or not. The cycle will continue long after every human being alive tonight has died, long after the last building we have built has crumbled, long after the last record of our species has faded. But you are here now. The sky is clear, or clearing, or will clear. The moon is above the eastern horizon or climbing steadily higher, the same moon that pulled the tides that may have cradled the first chemistry of life, that steadied the axial tilt that gave this planet's climate the long stability that complex life required, that lit the nights for every human being who ever hunted or planted or prayed or loved or looked up and wondered. The flower moon, go outside, let it find you.